Hi, I'm Akhil, and today I'll be taking you through our paper titled DNDNet Reconfiguring CNN for Adversarial Robustness. Due to their power and prowess, nowadays CNN models are being used in a myriad of computer vision based solutions. However, some recent researchers have raised a question on the adversarial robustness of these models. To combat this vulnerability, researchers propose defense methods to safeguard the underlying model. The figure on the right shows how a defense mechanism is expected to work. In this research, we propose a defense layer which is able to defend the underlying model from gradient based adversarial attacks that claim to operate under black box and gray box assumptions. So, our proposed defense layer is the first layer of the CNN model, and it computes the kth root of the difference between the input image I and the constant A as A approaches the input image I. Here k is any natural number greater than 1. So by definition, the defense layer does not add anything to the network. It propagates the input image as it is to the subsequent layers. However, during backpropagation due to the formulation of the defense layer, the gradients with respect to the input images are lost. This prevents the generation of the adversarially perturbed images, and hence the underlying model is protected. We explain this process in detail in the main text of the paper. Here, I would like to highlight the four main properties of the proposed defense layer. First, it is benign to the network. By benign, I mean that adding this layer does not come with any compromise with the model performance. Second, the layer is flexible and it can be added and removed very easily to any convolutional network. Third, it is efficient. The proposed layer has no trainable parameters and hence it does not require any time to train or optimize itself. And lastly, it is effective. It is able to block the generation of perturbations by 100% for gradient based adversarial attacks in gray box and black box frameworks. The proposed defense mechanism has been tested on MNIST, CFAR10, and PaSC datasets, and it has been tested against the listed optimization, gradient, and classifier based adversarial attacks. We use many state of the art CNN architectures as listed in the table. We test our proposed defense layer by first fine tuning the network with our dataset, followed by attacking the network with and without the defense layer, and then feeding the generated adversarial samples back to the previously attacked network. Here we report the performance results of this experiment. It is evident that using the defense layer has had an impact on the adversarial capabilities of these attack algorithms. These algorithms are not being able to fool the system anymore. In this experiment, we report the learning capability of the network with and without the proposed defense layer. The results of the experiment prove our assertion that adding the layer has no impact on the learning capability of the network. Finally, in conclusion, the proposed defense layer prevents creation of adversarial perturbations by blocking the network gradients from the outside world, and in this process, it does not hamper the learning capabilities of the underlying network. I thank you for your attention.